Hello, students. My name is Shami Mitra, faculty member of Department of Electronics and Communication Engineering, Greater Kolkata College of Engineering and Management. Today, I am going to take the class of Embedded System Design. So let's start with the class. Embedded System. The code name is EC703B, and this is the lecture 14. So up to lecture 13, what you have described here, we have described the communication protocols, input output buses. We have described what the embedded system is, how it works. We have given elaborate in the introduction of embedded system. We have described what is the difference between microprocessor and microcontroller, how it works. We have described the communication devices. We have described ISA. We have described PCI, PCTX, different kind of protocols. We have described the USB bus protocol. So all of these things has been already described. We have already I have already described all the functionalities and all the importance and significance of all these components, and we have described it in the last 13 lecture. So this one in the lecture 14, and here from today's on, from this lecture, we are going to describe the real-time operating system. So before describing what is an RTOS is and what is the significance of an RTOS is, we are going to deep down. We're going to dig deep to understand the RTOS system. So before understanding RTOS system, we need to understand what is an OS, what is the operating system, what is the functionality of an OS, how it works, what is the basic feature of OS, what is the purpose of an OS, why it is needed, what is the significance of an operating system. So let's begin with the class. So first, this is the course that we have been spanned out, that this is RTOS, real-time operating system. Second one is OS components, for the components of OS. Third one, we are going to describe the tasks, and the fourth one, we are going to describe the synchronizations, how the tasks synchronized, and the fourth one is inter-task communications. That we are going to describe all these things in the upcoming lectures. In today's lecture, this is the start. This is the first one, and today's lecture we are going to describe the basic features of OS, how it works, how it begins, how it ends, all these things. So let's begin with next. Let's go to the next slide. So this is the thing we are going to understand here. What exactly is an operating system? Why do we need an OS? How would the OS would look like? Is it possible for a team of us in the room to create an OS of our own? Is it necessary to have an OS running in an embedded system? Will the OS ever stop at all? So all of these things we are going to describe here. So first of all, we are going to understand what are the types of OS. So as I have already described in the previous lectures also, that OS can be two types as follows. First one is general purpose operating system that we have basically used in PCs. Second one is real-time operating system. That real-time operating system are also being used in basically are in use of an embedded system. So general purpose operating system are basically used in PCs, and the real-time operating system are basically used in embedded system. So now the second one is where and all the OS can run. One is in PC, second one is server, and the third one is an embedded device. These are the things. And the OS characteristics are these are the important factors that we need to discuss here, that how the OS characteristics works in PC, server and embedded system. So first we are going to discuss about the size. So from the name of the server, what is a server basically means? A server is a storage. Basically there are n number of devices are there to support the storage system. There are n numbers of memories, n numbers of processors are being in use to handle the server. So a server is basically the OS type in case of a server. As we have understand that the server is basically of a huge size. It has a very complex architecture. It has very difficult software are being used to maintain a server, where n numbers of data are being scattered around. So it is logically understandable that the size of a OS in case of server is much on a higher side. If we consider it with a embedded system, it is easily understandable that Okay, so we are understanding the size of our OS type. So next one we are going to describe is about the user interface. So user interface of a PC is in case of user interface, it is in a higher side. It is very much understandable that if you are talking about server, the purpose of a server is to store n amount of data. So user interface is not the priority of a server, but if you're talking about PC and embedded system, the user interface is the most important feature of a PC and embedded system. So embedded system basically has been designed for very limited purpose. Very limited functionality can be performed. Limited function can be performed in case of embedded system. So all such as example of a washing machine, microwave, all of these things are embedded system. So it is particularly the embedded system is a particular thing which is being designed for user interface. So in case of PC and embedded system, the user interface is lot more required. But in case of server, as you already know, the server is not being designed for user interface. It's basically designed for data storage. In amount of data has been stored and amount of data needs to be processed. All of these things. So the data manipulation and data data manipulation are being done in case of in a server. So in case of server, the user interface is not significant characteristics in server OS. So now if we're talking about the security, the PC and the server, in case of PC and server, the security required for PC and server is on a much higher side. If you're talking about embedded system, the security is not being much of concern, because suppose there is a security breach in case of an embedded system design or an embedded system, what will happen is that, as you have already known, that embedded system is basically designed for very specific functionality. So suppose there is a breach in the security of an embedded system, the person who breached the embedded system is not going to perform suppose a business hack, or it can't hack account. It is suppose in case of embedded system, the security it's important, but it is not been a far more important thing in case of embedded system, because it's manageable, because it only do very few functionalities are being performed by an embedded system. So security in case of PC and server is in a much higher side, but in case of an embedded system, the security of that is not much of a higher side. So now if we are talking about the reliability of server is a much more important factor, because suppose there is a reliability issue because of server, suppose there is a damage of data, it will cost a worth of crore of rupees will be go on vain, will be gone in vain. So the reliability in case of a server is utmost importance. But if you are talking about a PC or embedded system, the reliability is required, is very required, but it's a manageable amount. So it is not as important as in case of a server. And the same thing it will be applicable for if you are talking about the cost of PC, server and embedded system. It is very much understandable that now the server is a space where huge amount of data are stored or manipulated. So the amount of architecture, the design of the architecture, the size of hardware is much higher. The number of software that has been used in server is of a higher quality, the higher value, higher end software and hardware has been in work to manage a server. So the cost of a server, it has no match. If you consider PC and embedded system, it has no match to the and now if you compare the PC and embedded system, it is very much understandable also that in case of PC we use a general purpose processor. So and in case of PC we use application specific information processor or application specific integrated circuit. So it is also been understandable that in case of PC, the general purpose processor that has been used are of complex architecture are in play, and in case of embedded system, the architecture that has been used are not that complex. if you consider PC and embedded system. So it has been easily understood that the cost of a PC is much higher, irrespective of embedded system. So these are the types of OS, the OS characteristics that we need to understand. We need to have a pan out view of PC, server and embedded system. So we have already got that. So let's go to the next slide. So let's go to the next slide. So this is next segment that we are going to understand is the OS responsibilities. Now, what are the OS responsibilities? The first one that I am going to describe is the naming services. First one is username. Second one is the name distribution. The third one is name resolution. Fourth one is system addresses, system routes. So these are the four factors that has been managed or handled by OS. The second one is the file service. In case of file services, the OS file service collaboration, directory services, transaction services, and access services. So in case of file services, the responsibility of OS is the file service collaboration, directory services, transaction services, access services. These are the things. Now the third one is a resource allocation. Now resource allocation is an important factor. The responsibility of OS is also it's an important thing that OS take control of, is that suppose we have provided with a complex program that has been fetched, has been decoded, and according to the program that all the instructions are being decoded, and according to that the program will be executed. So the data will be fetched and the processor will process all the data that are all in play. So now to manage all those operations properly, we need to allocate the resource according to the process, according to the data that are being handled, according to the code, according to the instruction set, according to the instruction that are being already provided with. So the algorithms for load sharing, the algorithm for load balancing, the process migration coordinations, all are these three things are wholly or solely the responsibility of operating system. The fourth one that I want to describe, I have already been described all the process management things, that operations on local process, operations on remote process selection for migration, process migration coordination, all of these things. They are the process management part are being also being handled by OS. The fourth one, or basically the fifth one, is deadlock management, that I am going to describe. All these things I am going to describe in the upcoming lectures. What the deadlock management is. The deadlock detection and deadlock recovery is a very important factor that OS basically manage or handle. The sixth one is the process synchronized management. The same thing is basically the event ordering, concurrency control. All these things will be also the responsibility of OS. The inter-process communication, IPC, inter-process communication components, inter-process communication primitives, all are being handled by OS. And another one is the IPC support protocols. The inter-process communication support protocols also are the support protocols interface to microkernel. We are going to describe all the what is semaphore, microcontroller, all we are going to describe. And another one is the security, the access control, the resource protection, communication security and authentication, capabilities access list, key management, information flow control, data encryption protocols, kernel security. All are the list goes on, that the security part also being handled by OS. Another one is the coordinates, security, communication, resource management, service provider, file system, device access, system utilities, and system services. All are being managed by OS. These are all the things that is all other sole responsibility of OS. So let's go to the next slide. So in this segment, we're going to understand how the OS works. What is the how we initialize OS, and the step by step we're going to understand how the total process of OS is completed. The first one is after we switch on the power. After the power has been supplied to the PC or the embedded system, So embedded system design in embedded system, any system basically with processors or with ways. It the first thing the processor unit is loads the boot program from the read-only memory, or it would be very specific to say from the basic input-output system or BIOS in a form of acronym. The BIOS from the BIOS of PC, the CPU loads the boot program. Now, what is the boot program? The boot program, the function of a boot program is to examine or checks the machine configuration, the number of CPUs, how much memory, number of and types of hardware devices. It means basically boot program understand the configuration of a machine. So how many processors are being attached, what is the memory, the number and type of hardware devices, all of these things are being examined or checks by the boot program. The second one, the boot program is to build a configuration structure describing the hardware, builds a configuration structure describing the hardware, and loads the operating system and gives it the configuration structure. So the boot program, what it reads or understand the structure, the hardware, and after that it loads the operating system. It loads the operating system, gives it the configuration structure. So these are the first few things that are being done by OS. So let's go to the next slide. The next part is that after the basic process have started, the OS runs the user programs if available. If the user programs are available, it runs the user programs, or otherwise it enters the idle loop. It means if there is a user program already been available, it will run the user program. If it is not available, it will enter to an idle loop where it will still stand. And in the idle loop, the operating system executes an infinite loop basically. In Unix, it executes an infinite loop. How? The OS performs some system management and profiling. And the third one is OS halts the processor and enter in a low power mode. So if there is a user program, it will run the user program. Otherwise, it will enter the idle loop. In that idle loop, what really happens is that the OS executes an infinite loop. The OS performs some system management and profiling, and the third one is OS halts the processor and enter in a low power mode. So these are the functions. Now, if we move to the wake up part where the OS wakes up, what it done is that interrupts from hardware devices. It interrupts from it will interrupts from hardware devices, exception from user programs, system calls from user programs. All these things, if OS are in idle mode, it will execute all these three things, or it will the work in progress of our OS will be in these three steps. Now, if suppose there is a user program is available, what will happen is that it interrupts from the hardware devices, exception from user programs, or system calls from the user programs. All these things will be happen if all these things happen if OS wakes up. The two modes of execution. One is the user mode, which is less privileges, and supervisor mode, the unrestricted access to everything. This is the supervisor mode, where the supervisor will have the access to everything. There is the unrestricted access to everything. So let's go to the next slide. Now this is the control flow in OS. So the control flow of OS works as we have understood that first the boot program loaded in the main function. So the initialization happened. Then the operating system module, the supervisor mode. If it goes to the supervisor mode, it will have access to everything basically. How it works? That it will access to interrupts, it will access to the system calls, it will access to the exceptions, and the return to user mode. Now suppose operating system modules is a supervisor mode, it will have all the access. Now if suppose it is in user mode, what will happen? The interrupts from the device, system calls, and the exception, all these things can take place. So this is the total control flow of an OS. If it is in a user mode, it can handle the interrupt, system calls, and exception. If the operating system module is in the supervisor mode, it will be in the control of everything. So these are the differences. So let's go to the next slide. Now the control flow interrupts, how the interrupts works. These are the exceptions, system calls, and so in this segment we're going to understand what are the interrupts, what are the system calls, and what are the exception are. So let's start with the interrupts. The hardware calls the OS at a pre-specified location. OS saves state of the user program. It means the operating system in wherever it is, in which state it could be in, it saves the state, it pauses the state, it goes according to the pre-specified location, because as the hardware calls the OS, so the pre-specified location in the OS will be in this pre-specified location. Next, the operating system identifies the device and cause of interrupt. Response to the interrupt, as it very much clear, the operating system restores state of the user program. The operating system restores the state of the user program and execute and return to interface instruction to return to the user program. The user program continues exactly at the same point it was interrupted. Now, if the interrupt as saying there will be another process it needs to be run, it will run that, and until that the OS, it will be the user program state will be in idle situation. After the interrupt, the function of the interrupt completed, the user program continues exactly at the same point it was interrupted. So let's go to the next slide. The control flow exceptions, how the exception works. Now the same thing here, the hardware calls the OS at a pre-specified location. OS identifies the cause of the exception, divided by 0 or other. If user program has exception handling specified, the OS adjusts the user program state so that it calls its handler. Execute an RTA instruction to return to the user program. If user program did not have a specified handler, then OS kills it and runs some other user program as a handler. Let's go to the next slide. The control flow system calls. Hardware calls the OS at a pre-specified location, the same process. The user program execute a trap instruction, system call. Hardware calls the OS at a pre-specified location. OS identifies the required service and parameters. OS executes the required service. OS sets a register to contain the result of a call. Execute an RTA instruction to return to the user program. User program receives the result and continues. So these are the control flow system calls. So these are the three control flow. The first one is the interrupt, second one is the exception, and the third one is the system calls. So this is the end of today's lecture. The summary will be that an OS is just a program. It has main function which gets called only once during boot. Like any program, it consumes resources such as memory, can do silly things like generating an exception, etc. But it is a very strange program. It is entered from different locations in response to external events. It does not have a single thread of control. It can be evoked simultaneously by two different events, system call and interrupt. It is not supposed to terminate. It can execute any instructions in the machine. So these are the summary of the operating system. So today through this lecture we have a very clear picture of an OS. So for the next lecture we are going to start to understand, or we will get into the understanding of the deep knowledge of an OS. So thank you. We are concluding here. Thank you.